All right, kids, here's your semester final review. Enjoy. All right, and so we're going to go back to the beginning of the year with limits. And remember, a limit is something where we want to know what the value of y is doing as x approaches a specific number. And we usually want to investigate what happens when x gets really close to that number but doesn't actually touch it. Well, we start you off with a softball here because we want to know the limit as x approaches 6 of this radical. And hey, guess what? As long as we substitute 6 in there, we won't get anything that's undefined. And so we can do that then because, hey, if we can substitute in and find out exactly what the limit is, that's what we want to do. It doesn't always work out that way, but in this case it does. So simply take this 6 right here that x is getting close to and replace the x's with that 6. So what you're going to end up with is 6 squared plus 12 times 6 plus 36. All that's under the radical still, so I'm just simply working out that part. This is 36 plus 72 plus 36, that's going to be 72 plus 72, which is 144. So we're ultimately working with the square root of 144, which is 12. And that is it. That's all you have to do. That's how easy they are. And rock on, rock on. All right, on this problem, what we want to do is look at the limit as x approaches 0 from the left, that's what the little minus sign there means, from the left, of the graph of 10x over absolute value x. So here's a graph of 10x over absolute value x, and we'll notice right off the bat there's a big discontinuity at 0. So we'll also notice off the bat that if I try to put a 0 into this, it just doesn't work. If I put 10 times 0 over the absolute value of 0, I get 10 times 0 over 0, which is 0 over 0, and we don't know how to handle that. Okay, that's in the realm of things that we're not sure of yet. But I do know for a fact I can't have 0 in the denominator, so now I have to look at the graph. And the graph tells me, the limit tells me to look at the graph as I come in from the left, and if I'm looking for a limit, I want to know what the y value is doing as x approaches a specific number. In this case, x is approaching 0 from the left. So the question I ask you is, what value is y getting close to? Well, y is 10 right here, and it's 10 right here, and it's 10 right here, and it's 10 all the way in, and these are all negatives, by the way. And it's negative 10 all the way till we get to 0, and then it's nothing, and then up here it's all positive 10s everywhere we go. So the question remains, what value of y am I approaching from the left? As you'll look, everything on the left-hand side of the origin is all negative 10. So in this case, our limit is negative 10. And that's it. That's all you got to worry about for this particular problem. All right, with this problem, we want to find points of discontinuity and then identify what that type of discontinuity is. And when we're looking for points of discontinuity, what it really helps to do is factor everything on the top and bottom of a rational expression. So in this case, we've got x plus 3 on top. He's already factored. There's nothing left to do there. On the bottom, we're going to factor this guy to x and x. And then what times what is positive 30? That add up to be negative 11, and that would be minus 5 minus 6. So look and see if anything will cancel out. Nothing does. And so to find discontinuities, direct your attention to the denominator. That is where discontinuities are going to occur. You can have a 0 in the numerator. It's not a problem. Does not create an issue. So I've got discontinuities when x minus 5 equals 0, because that gives me 0 in the denominator. And I have a discontinuity when x minus 6 equals 0. That gives me a 0 in the denominator. So x equals 5 and x equals 6. Those are the two places where I am going to have problems with my domain. Now, the next question says to identify what kind of discontinuities they are. And what's going to happen is, if you just think about what we're doing here, we've got this graph over here, and at 5 we've got this vertical asymptote, and at 6 we've got a vertical asymptote. And since there's that vertical asymptote in the way, I don't know what the graph is doing, but I know it's not crossing the vertical asymptote. So it's doing something along the lines of up here and down here and back up here again, and I don't know, it's something like this, okay? And so what that tells me though is these graphs aren't going to touch. These three different pieces aren't ever going to touch. And I don't know if this particular graph makes this particular shape, but I do know that with all vertical asymptotes, those are imaginary walls that just can't be broken through. So when I look at the type of discontinuity here, since these 2 points will never touch, and since as we get closer and closer to the vertical asymptotes from each side, the graph will either go up to positive infinity or it'll go down to negative infinity, then the type of discontinuity we're going to have is an infinite discontinuity. And remember, there's a couple different types you could have. You could have a jump, so our graph would do something like this. Okay, that's a jump discontinuity. You could have a removable discontinuity, which is just a little simple hole in a graph, just like this. It's removable. We've got this infinite discontinuity. So those are kind of some different ways that we could have a discontinuous function. Jump, removable, and infinite. Okay? Alright, with this problem what we want to do is we want to find the tangent line of x squared minus x at the point x equals -3. And in order to find a tangent line, any equation for any line, you need a point, and we need that point to be an xy for us, and you need a slope. And right now all we know is the x-coordinate is 3. We have nothing else. Well, to find that equation of a tangent line, what we're going to do is we're going to take the derivative. And early on in the semester we talked about the actual definition of derivative. I'm more concerned right now that you understand what derivative does and the different things that you can use it for. And so what we're going to see is we can take this derivative, and this derivative is the equation to find the slope at any point on the line x squared minus x. The point we're really interested in is -3. So I want to plug in -3 everywhere I see an x. That gives me -6 minus 1, which is -7. That's my slope. That's this guy right here. So now he's not a question mark anymore. He is -7. And when we do this, the other thing that we have to have is a point on the line. Well, I've got an x-coordinate, and in order to find a point on a line, I just plug my x-coordinate into my original equation. So -3 squared minus -3. It's going to be 9 minus 6, 9 plus 6, which is going to be 12. And so now that I've got a point, and I've got an x-coordinate, and a y-coordinate, then I can go ahead and substitute everything back around, and so my point then becomes -3, 12. It's -3, 12, right? 3, 9, 9 plus 3, 12. And so to write the equation of a line, I'm going to use good old-fashioned point slope. It's the easiest one to use. It's most handy. You can use it all the time. It's y minus y1 equals m times x minus x1. So here's what that looks like. So I substitute in the values that I'm going to have. So it's going to be y minus the y-coordinate, which is 12, equals the slope times x minus the x-coordinate. And you can leave it like this if you want to. It's totally fine. If you're insistent on having an equation that says y equals, just move the 12 over. Y equals -7 times x minus 3, or I'm sorry, plus 3, plus 12. That's good enough for me. And if you want to go one step further and combine everything together, I don't have a problem with that either. Knock your socks off, but it's not really necessary for this problem. However, depending on your teacher, always check with them and see where they want you to stop. But this is the equation of a line, and I am happy for my kids if you can get that far. Alright, on this particular problem, we want to know whether or not the derivative exists when x equals 0. So that narrows down the part of the graph we need to look at. We need to look at everywhere that x is equal to 0. So just go with me here as I give us a dotted line to investigate. We're looking right here on this line where x is equal to 0. And there's four things that happen that prevent you from being able to have a derivative. One, you could get a cusp. If you have a cusp, which is a shape that looks like this, you cannot have a derivative. Two, if you have some sort of discontinuity, any kind of discontinuity at all, and it doesn't matter what it is, you can't have a derivative. So if I have this situation, no deal. If you have a vertical tangent, something along the lines of a graph that looks like this, then you cannot take a derivative at that point, only at that point for all of these. And the last one is a corner. If you have some sort of corner situation that has developed over your graph like an absolute value. So these are the places you can't take derivative, but you can only not take derivative at the places where these things occur, at these actual discontinuities, at the vertical tangent, at the corner. Everywhere else you can take a derivative. So look at our graph. We've got this shape right here. What is the situation that keeps us from being able to find the derivative when x is 0? And on that one, it really matches that guy. So we would say for this particular problem that a vertical tangent is what prevents us from keeping or from being able to find a derivative. Now, having said that, if you look from right here all the way up to but not including 0, you can take a derivative. If you look from 0 all the way out here and you can keep going, you can take a derivative. At 0, at this middle point right here, that's the only place you can't. And you can't because it's a vertical tangent. Alright, on this problem we want to just find derivative of y. And there's a couple of different ways that you could do this one. You could use the chain rule and put that together with a product rule and then the negative exponent. But I think on this particular problem, the way it's set up, it's just going to be easier to go ahead and find the derivative using the quotient rule. And remember, quotient rule is low d high minus high d low over low low. And for this particular problem, I would choose to use the quotient rule. Can't give you any exact specifics why. I just know that for me personally, it's just easier to deal with. Okay, so let's find that derivative. Y prime is equal to low d high, so x squared minus 5x plus 3 times the derivative on the top, which is just 3, minus high, which is 3x minus 9, d low, which is 2x minus 5. Now, when you're working with quotient rule, basically any time in general in calculus, when you're doing anything at all and you throw a minus sign in there, automatically add a bracket. You're almost always going to have something else occur behind the minus sign, which you need to keep track of. It's very seldom will you write down something like minus x squared, or minus 2x, or minus 4. It's usually minus and then a whole bunch of other stuff. So always put a bracket in there after you put a minus sign when you're working in calculus. Right here is where I'm talking about. Always put that bracket in. And you'll notice on this particular problem, we've got stuff in there behind the bracket as well. Okay, so there's the setup. Now we got to do the cleanup. There's no need to FOIL out the bottom. Probably nothing will go away anyway. So on the top though, we're just going to distribute that 3. That's going to give us 3x squared minus 15x plus 9 minus, and then go ahead and FOIL these two guys out in here. So keep your bracket going for just a little bit longer, and you get 3x, 6x squared, negative 9, negative 5 is 45. And then in the middle, you're going to get negative 18 minus 15. I got that to be negative 33. Over x squared minus 5x plus 3 squared. Okay, then just combine down, and this is 3 of course, even though right here it's hard to tell. So now just combine all the things together that have the same variable and exponent. So 3x squared and 6x squared become negative 3x squared. Negative 15x goes with negative 33. It's going to give us negative, actually positive 33. So that's going to give us 18x. And then plus 9 minus 45, negative 36. And you can factor 3 all of that out of all that if you want to. There's no need to. And then on the bottom, x squared minus 5x plus 3 squared. That's what y prime is. So there you go. That's your derivative right there. That's quotient rule. Quotient rule really isn't too bad of a guy once you get used to him and you use him properly, and he enjoys. He likes it when you use derivative and use quotient rule. It's a good thing to have in your calculus bag of tricks. All right, question 7 says to find the slope of the tangent line to the curve at the given value of x. So this is similar to a problem we worked out already in this lesson. And if we want to find the slope of a tangent line, anytime that we're going to find the slope of a tangent line, we need to find derivative. The derivative of this particular problem is 2x minus 7. Now, this is the equation to find the slope of a tangent line at any point. At any point, doesn't matter where, just as long as we're on the curve x squared minus 7x. Well, we're really interested when x is equal to negative 3. So what are we going to do? We're going to take a negative 3 and we're going to drop it right in there for that x. So 2 times negative 3 minus 7, negative 6 minus 7, negative 13. This is what f prime of negative 3 is. This is also the slope of a tangent line. Now, they didn't ask us for an equation on this particular one, but we could certainly find it quite easily. In fact, we've already got an x-coordinate and we've got a slope. And to find an equation of a tangent line, you need a point xy and you need a slope. And we've got 2 of those 3 things. So to find the third, we're going to go ahead and write the equation of a tangent line. To find a third, back to our original equation, and we're going to substitute in that's not a prime, let me clean that up. We're going to substitute in a negative 3. So negative 3 squared minus 7 times negative 3 is 9 plus 21 is 30. So that's your y value. So I've got x and y. So y minus 30 equals the slope times x plus 3. Remember, we're going to use the point slope formula. It's a lot easier to do. It does give you the equation of a line. If you insist on having an equation that is a y equals equation, and that's how it's got to be, that's how you were taught in Algebra 1, and by gum and by gollies, it's got to be y equals, then just move your 30 over. And that's all you need to do. There's the slope of the line, x squared minus 7x, at the point x equals negative 3. And on top of that, you got the equation of the line that runs through that particular point as well. All right, given the distance given a distance function, s of t, which is distance or position, a lot of times it's a position function, is equal to t squared plus 3t plus 30. S is in feet, t is in seconds. Find the velocity function and the acceleration function. The cool thing with position, velocity, acceleration is they're all related by derivative. So if I have s of t here, and I have t squared plus 3t plus 30, if this is what I have, when I take the derivative of that, s prime of t, that gets me the velocity function, the instantaneous velocity function. Well, the derivative is going to be 2t plus 3. That's it. That's all there is to it. And so if I take the second derivative of t, that's the same thing as the derivative of velocity, which is going to give me acceleration. So derivative of velocity would be 2. And that's the acceleration function for this particular guy. It didn't work out any more difficult than that because we started with a second degree equation. If we had started with an equation of third or fourth or fifth degree with some other variables tossed in there, we would still have something in the acceleration equation with variable in it. If we had a position function that had a negative exponent, we would still have something with the acceleration in the acceleration part as well. So it's not uncommon to get a constant for acceleration. It's also not uncommon to have some sort of wacky function in there that allows us to take derivatives several times so that we would have a nice, cool looking function for velocity and acceleration. But that's all there is to it. If we know position, we can find velocity by taking derivative of the position, and if we know velocity, we can find acceleration by taking the derivative of that. Here's another derivative problem, except this time you might notice that x and y aren't all together in one equation. There's t's running around. And not only that, we want to find an equation for a line tangent to this at the point t. So let's dive in. I've got to take a derivative of a parametric equation. So remember, a derivative is the same thing as dy dx. So check this out. If I put dy dt on the top of a fraction and dx dt on the bottom of a fraction, now why am I doing that? I've got x, I've got y, I've got t. Okay? So, but look what happens. What are your rules whenever you're working with fractions? Your rules say that when you divide by a fraction, you multiply by the reciprocal of the fraction you're dividing by. So the reciprocal of dx dt is dt dx, and check out what happens on this bad boy right here. dt's cancel, and I'm left with dy over dx. Thank you, Leibniz, or Isaac, or Huygens, or whoever it was that created this particular way to show a derivative. He's a lifesaver on problems like this. So what we're going to do is we're going to find y, which is t squared. We're going to find x, which is 6t squared minus 3, and we're going to find the derivatives of these puppies right now. So y prime is equal to 2t, x prime is equal to 12t. And then we're just going to use this formula we discovered. So I'm going to put y prime dy dx is equal to y prime over x prime. And that's going to be equal to 1 over 6. Let me double check my math, and that's correct, 1 over 6. Okay, so with 1 over 6, what's that mean? That means that that's the slope of my line at the point, at any point. And what point are we interested in? We're interested right here in this cool guy. Well, I've got a slope already. That is my slope. This is my slope. There's no specific thing to do to it. I don't have any variables running around. It's always going to be 1/6. So to finish my problem off, I need to find my y coordinate. They give me t. So when I put t in, I get 1. To find my x coordinate, I do the same thing. I put in my value for t and run my math here. So I get these coordinates to be 1 and 3. And so in order to write the equation of a line, I'm going to use y minus y1 equals m times x minus x1. All right. And look, I've got everything I need. Here's m, here's y, here's x. So y minus 1 equals 1/6 times x plus 3. If you had that teacher growing up and that teacher said never, 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 ever have a, by the way, this should be a plus 3 right here. Never, ever have an equation that doesn't say y equals, then go ahead and move over the 1. And how do you do that? You just add it to both sides. Y equals 1/6 x minus 3 plus 1. That's it.